Alright, hello everyone and welcome back to the channel. So today I've got a new video for you, one of the most dreaded chapters because of the numericals involved, that's nuclear physics and radioactivity. There's also some questions related to this which were asked in the past year. Students were not aware that that was even part of the syllabus. So I thought why not make a video on this and clear up the air. So nuclear physics and radioactivity is unit 5 of your syllabus that we'll be starting with today. The first part related to nuclear physics is pretty straightforward because you study a lot of this in chemistry too. So all matter is made up of very basic atoms. Atoms comprise of a positively charged dash at the center being orbited by negatively charged dash. So we know this at the center is the nucleus and they're being orbited by negatively charged electrons. And we also know this, and this is what will be covered in the points to come, that the nucleus is positively charged because of the protons there, because it contains protons and neutrons. So nucleus consists of electrically neutral neutrons, as the name goes, and positively charged protons. The force for electrons to orbit the nucleus is provided by the electric force of attraction exerted by nucleus on the electrons. So this is basically the idea of circular motion, which is that if I see this electron here, if this is an orbit, so circular motion says that the force required for it to be in orbit must be towards the center. So this is the force, this is also the direction of the acceleration, which is towards the center, and in this case it's provided by the electric force of attraction exerted by the nucleus on the electrons. Because the nucleus is positively charged, electrons are negatively charged, so they would attract. So the nucleus would attract the electrons, and needless to say, for the orbit to happen, this must be moving tangential to the path of the circle being traced out, and this causes the direction between force and velocity, or you can say between acceleration and velocity, to be 90 degrees, hence fulfilling the conditions for circular motion. So Newton's third law also applies here, as we did also with forces in unit 1, which is that if this is the force which is applied by the electrons, by the nucleus on the electrons, Ne, so there is an equal force applied by the electrons on the nucleus in the opposite direction. This is Newton's third law in this context. This is Fen, and both of these are equal. They do not cancel out, and the very basic reason is that because they act on different objects. This one is acting on electrons, this one is acting on the nucleus, right? So they're different objects overall. Alright, then this table is again something that you've seen with me in static electricity. So for the particles, the relative masses, the relative charges, so protons and electrons have equal charges, only that proton has a positive charge, electrons have a negative charge. Protons and neutrons have approximately equal masses, so their relative masses are the same, and electrons have 1 over 1840 times the mass of either a neutron or a proton. An atom is electrically neutral because it contains equal number of dash and dash. So we know that the particles which contribute to charge are protons and electrons. So they have an equal number of protons and electrons. Sometimes and occasionally this is asked, it is a syllabus learning outcome of yours, which is to say that what is a nuclide? A nuclide. So this is just a form of an element. So this could be an atom on its own. It could be an ion which is formed by the transfer of electrons. So nuclide is just a way of representing what it is. So it's just a form of an element. Alright, so the nuclide notation is written like this. This is the symbol for your element. This X is the proton number, which basically tells us that the number of protons that are there in this atom, and Z is called the nucleon number, And nucleon number means this tells us the total number of nucleons. So nucleons are the particles in the nucleus, so that consists of protons and neutrons. So the number of protons equals x if z is the total number of protons and neutrons, and if I need to find out the number of neutrons only, I would subtract the protons from that, which is what is written here. And again, for an atom, number of electrons and protons are equal. Ions are formed by the transfer of electrons, right? Electrons are the ones which are loosely held in the orbit outside. The proton is pretty tightly bound inside the nucleus. So if an atom gains electrons, it now has more electrons than protons and hence an overall negative charge. So if it gains electrons, previously when it was an atom, the electrons and protons were equal. But now if it has more electrons, then this means that it would have an overall negative charge. This is how it's represented. Similarly, if an atom loses electrons, previously it had an equal number of protons and electrons. If it's now lost electrons, it has more protons, or I can say it has less electrons. So this results in an overall positive charge. So that's the idea here. And we'll be using this in this small example, kind of what you do in like your pretty first chapters in chemistry. So for each of these nuclides shown, you have to find the number of protons, neutrons, and electrons. And it's pretty easy if you go in this exact order, because it's in the order of what's easier to see and what's more difficult to see. So for the first one, I know that proton number is just what's written here. So the number of protons is 3. The total number of neutrons and protons is 7. So subtracting the 7 and 3 gives me the number of neutrons. So that's 7 minus 3. This is equal to 4. And because this is an atom, there's nothing here with a plus or a minus. So the number of electrons must also be equal. So that's also 4. Moving on to this one, the number of protons is 29. Again, the easiest thing to see. The number of neutrons would be 63 minus 29. That's 34. And the number of electrons in this one. So for this to have a 2 plus charge, this means that the number of protons are 2 more than the number of electrons. So 29 minus 2, this must be 27. C, the number of protons, 17. The number of neutrons, 35 minus 17, which makes this 18. And the number of electrons, again, this has a negative charge, so it means it has just one more electron than a proton. So 17 plus 1, that makes this 18. Pretty straightforward. The idea of isotopes are atoms of the same element that have the same number of protons. So that's why there is the same element, because the protons are the identity of an element, but they have different number of neutrons. All right, so that's the idea of isotopes. On to the next thing, which is alpha particle scattering. Some of you might have also studied this as the Rutherford experiment in your syllabus, but this is the official name that the syllabus uses. So you have a source of alpha particles which is incident on a very thin gold foil, and then this shows deflections in some directions. And the purpose of a thin gold foil is that it only experiences a single deflection, and we'll get to this in a moment. It's kind of an advanced concept, but still I've mentioned this. So alpha particles, all you need to know about this for this experiment is that they are a helium nucleus basically. So a nucleus means it's the atom minus the electrons. So you just have you have a total of 4 nucleons, so that's 2 protons, and 4 minus 2, 2 neutrons. So that's what this is. This is incident on a thin gold foil, and this is what we see. Most of the alpha particles pass through undeviated. Some are deflected through large angles, and even fewer rebound back along the initial path that they were sent out on. This is shown in this diagram. So most of them, they just go through undeviated. Some are deflected through large angles like this, and some rebound back along the original path. Now, each of these relate to an observation, and for each of those observations, we get some conclusions about the structure of the atom. So the purpose of the alpha scattering experiment is to get more information about an atom and how the particles in an atom are organized. So the first thing that I see is that most of the alpha particles remained undeviated. So this means that because alpha particles were positively charged, if most of these remained undeviated, then they didn't even know that they were passing through an atom. So that's why the conclusion that I get from this one is that most of the atom is empty space. Next. 2, we see that some particles deflect through large angles. Now we can see the direction of deflection from this diagram here. We know these are positively charged particles, right? So for them to be deflecting away, for them to basically be repelled, what charge should the nucleus have? Right? Because if you also look at the geometry of this one is slightly closer to the center as compared to this one. So this means that the nucleus must have also been positively charged to repel these positively charged alpha particles like this. So I'd say that what this tells me is that the nucleus is positively charged. All right, so the nucleus is positively charged. The third one, only very few, and you can see that this is even closer to the center here, only very few rebound back along the original path. So the idea is that if this is your nucleus, then you can see that only these of the particles were close enough to actually almost be in the line of the nucleus. In other places, the other particles were not as lucky to be so close to the nucleus. So because they come so close to the nucleus, and if these are also positive charges still, so these experience a very, very strong force of repulsion because the distance between them is so less. So what we get from this is if only few particles were observed doing this, then these were the lucky few who were fortunate enough to be so close to the nucleus. Because, and this is the conclusion, that the nucleus is very small. So very few particles rebound along the original path. So this tells us that the nucleus is very small. So that's the idea regarding the first part of this chapter, which is nuclear physics. So in the following videos, we'll be going over the radioactivity part as well. See you there.